All right, let's get started. This is lecture 24. So we're going to go through several examples where we are asked to calculate the inductance. In the first example, as you can see here, there is a coil. So the black line is the coil where current I1 is flowing. So this is the coil. And you can see that the I1 is flowing that way. And although it's not very obvious in this picture, if you apply your four fingers along the current path in the coil, you'll notice that due to the direction of the current and where the coil is aligned, the magnetic field is pointing towards the right side. So you can see that the B field is already indicated by the problem. And the coil radius is R, and it has a number of turns of N per the length of L. Okay, so each length of L, there will be N turns. So the longer, the more turns you'll get. But per length turn is N over L. So the example is asking us to find the self-inductance per unit length of a long solenoid in air. So the in air means that there's no core material. So as shown in this picture, there's nothing inside the coil. It's all air. So in that case, the mu r, the relative permeability is 1 because it's air. And again, there are n turns per unit length. So the first step is, according to the 6 steps that we discussed last time, the first step is to figure out a coordinate system and express the magnetic flux density accordingly. So in this figure, we're going to apply a cylindrical coordinate system where the r axis is pointing downwards. Okay, so this would be your circular bottom phase, bottom plane for the cylindrical coordinate system, and the x-axis, the horizontal axis, will be the z direction. Okay, if you think about a 90 degrees tilted cylinder, this is going to be your cylinder, right? And so in that case, the B field is going to be in exact alignment with the z-axis direction. So the B field can be now expressed in terms of um, AZ because it's going in the direction of the z-axis as shown here. So the B is BZ times AZ, just because the coordinate system that we chose is cylindrical coordinate that is 90 degrees tilted. So the next thing is to figure out what the B field is, and therefore we're going to plug it into this equation, Ampere's law, where if you do a line integration of the B field, and if it's a closed loop, then that would indicate the amount of current that is enclosed by that imaginary closed loop. Okay, so you can see that in our case, if you look at this picture, you'll see that the loop is now around, enclosing a bunch of coils, okay, and the surface area of this loop is going to be punctured by these number of turns that is going through this imaginary loop. Okay, and so the length of the loop, I'm going to choose L, so the length of the loop is L, but the height of the loop will be so tiny that we don't have to think about it. In that case, the amount of current enclosed in that red box above is I1. So each of the lines that are puncturing this red box is I1, but there are n turns because it said so, right? There are n turns per length. And so the total amount of current enclosed by that red loop above is now going to be I1 times n. Okay, but it's going to be divided by L because we want to know, we know that's not the entirety, right? This is an infinitely long solenoid, so we can only express the number of loops per length. But anyways, the enclosed amount is this, and you need to multiply it with mu zero, mu naught, because it's air. In order to calculate this, integration, we know what the B expression is, right? It's here, but we need to know what the DL expression is. So DL is shown here, and you can see that it's also a function of Z direction. So that's why we have the AZ unit vector multiplied by a tiny portion of L. What it means is that we're running this way and running that way. Okay, we don't care about the vertical portions because we're going to reduce the box so thin that it'll barely enclose the currents like this. So we don't care about the vertical section, it's almost zero. So that's why when you do the line integration, you just have to care about this length and that length, and therefore the DL is DL times AZ. So now if you plug everything inside, plug it in here, and plug this guy into here, and if you rewrite, you'll notice that the AZs, there are AZs that comes from this and this, they multiply to become 1. And so you're left with BZ and DL, where DL is now going to be integrated from 0 to L because that's what we set over here. Okay, but that's for the positive direction, so meaning that when you're going this way, you have this part of the equation, but you have to return. So now you have to do a negative DL AZ and plug it in. So that's why you see a negative sign here, because you're now running this way. But the B is exactly the same. But you got to notice that, well, these two chunks of the equation represents this guy, and this is still equivalent to mu naught I times n. The L slash L, the L disappeared in this case because we already integrated over the length of L. Okay, so we exactly know that there will be n turns in the length of L because we are integrating from 0 to L. The other thing you need to note is that when you're moving this way, and when you're doing the integration for the B field, there is B field because B field will be contained inside the coil. Outside, there is no B field. I mean, in reality, there will be some because of leakage, but in this example, we assume that there's no leakage. And so outside the coil, there's no B field. And therefore, you have to scratch out this B Z to 0, so this part this part disappears. And therefore, if you look at this, and if you compute this, if you calculate this integral, then you get BZ times L, and that is equal to this part. Okay, and so if you now divide the L on both sides, you get N over L again, but that can be expressed in terms of a per unit length turn. So a small n, a lowercase n over here, this is a capital N divided by L. So that's the number of turns per unit length. And so you now know that, this is a scalar because it doesn't have a hat, but if you add a hat, then you have to multiply AZ to it. So it's a mu 0 I1 plus times lowercase n, which is n divided by L, multiplied by the unit vector in the z direction, because the B vector is in the z direction. Once you get the B field, we need to calculate what the flux is. So again, B is a flux density, so it's Weber per meter squared, okay, but flux is Weber, okay, there's no division by meter square. And so to do that, you just got to integrate the B field in terms of the surface. And if you do that, you will notice that the B field is over here, mu I1n, that's a B field, but pi r squared, which is the surface area of this coil. So the surface area of the circle is pi r squared, and that's where all the B field is. So the flux is pi r squared times the B field. Once you do that, that's the flux. But see where the flux is flowing through. All the flux is flowing inside this coil, right? So the coil, depending on the number of coils, the linkage increases, right? If you have like 4 coils, then it's 4 times the flux. If there are n number of coils, it's n times the flux. So you can see over here that if you need to, the next step is to calculate the flux linkage um, per unit length, and therefore you need to multiply the flux with the number of coil per length. Okay, that gives you this equation. You simply just multiply n over here and you get this equation. So this is the flux linkage per unit length. And the last step is to divide flux linkage per unit length with the current that generated the flux, okay, in order to get the inductance, because the inductance by definition is flux linkage per ampere. Okay, so you got to get rid of this guy, I1, because you need to, calculate the L, and that would give you the inductance per unit length. Okay, that the expression for that is this. So the inductance per unit length will be increasing if you have more number of turns per length, meaning that the lowercase n will increase, then L will also increase. And the other thing is if you increase the radius, so if the loop of this coil increases, if this is the coil, that is this big, then you'll have a larger self-inductance. So when you actually do experiments, and if you work at a lab or at a company later on, you need to keep in mind that the unit per unit length inductance of a coil will increase if you accidentally like place coils like this on the floor and do some experiments, right? Then you have this much of an inductance. But if you place this size of a coil, then you have less inductance because the radius is smaller. Okay, so this is a very useful equation, important one for you to understand. What if, so the second example over here is showing us a coaxial conductor. Coaxial means that you have a center conductor and this goes into the screen. Okay, it's running into the screen, and you have an outer conductor concentrically aligned. Okay, typically the outer conductor is grounded for safety, and the voltage and the current is flowing in the inside of the conductor. So this is called the coaxial cable, and sometimes they call it coaxial transmission line. Okay, so it has a solid inner conductor. So the inner conductor, the gray one, is a solid piece of metal carrying current, and the black circle, that's the case. That's a coaxial conductor, very thin. That's the outer conductor. So how do you find the inductance per unit length of this cable? Okay, even if you're given a piece of wire, I told you before that it has an inductance. Okay, it'll be small, but there is an inductance. If you have a coaxial cable, it will also have an inductance. All metal, all conductors that carry current will have an inductance. So let's see how to figure this out. So if you look at the side view, you'll notice that the center conductor is the gray shade and the current is flowing, and current is equally distributed. Okay, so the current is uniformly distributed. So if you calculate the J would be just uniformly, constant inside that conductor. And the inside conductor has a radius of lowercase a, and the outside conductor has a radius of lowercase b. First of all, if you align your thumb with the current, then your right thumb with the current, then your four fingers will wrap around like this. Okay, so you'll notice that the B field is going to be wrapping around like that, according to the right hand rule. And so, um, again, if you apply the cylindrical coordinate that looks like this, then the radius will be the R, and that would be your Z direction, and whatever is rolling around the Z axis will be the phi direction. And so in this case, the B field can be expressed in terms of the function of phi. So you have a unit vector of a phi that represents the direction of the B field, like that, and you have a constant that we don't know yet. Okay. So as the current is flowing, B field will be generated like this, and so, but if you look closely, current, thin amount of current is flowing at the very center, and also there are some current flowing off center of this central conductor, right? And so if you think about the current flowing at the very center of this conductor, that'll be generating the B field as well. And some other conductors flowing at the surface will also generate the B field. So even inside the thin conductor, there are locations that are linking with the B field generated by its neighbors, or even by itself. Okay, so we can dissect this problem into two sections where we investigate the B field that are inside the conductor, and of course the B field outside the conductor. Okay, because the B field is everywhere, so there are portions that exist inside the conductor, and there are portions that are outside the conductor. So if you focus on the inside of the conductor, okay, where the radius is from 0 to A, so radius is 0 to A, meaning that it's inside the gray material, the solid material. We need to apply the Ampere's law, and um, we will need to, first of all, when you apply the Ampere's law, you need to make sure that your contour, this imaginary contour that you decide where to put, has to enclose a current, okay, and be where the B field is. So in this case, I'm going to put the contour around the loop like this. Okay, that would be our contour. Okay, like that. That way, the red line, the contour is where the B field is, and it is also enclosing. It's getting punctured by this current. Okay, that way you can now write this equation where you have the B times L, and you do the integration, and that will be equivalent as the current the contour is enclosing. So that'll be I, because it said the problem told us that the current is I. The next step is to define what dl is. dl is a tiny portion of this length, right? So it's going to be a function of phi, and it's going to have r times d phi length. So r times d phi in the direction of the phi angle. So that'll be your dl. Okay, now we're going to plug this in here. And if you do that, and if you plug in the B definition, you get this equation. And because of the two a phi's will, multiply into one, we can get rid of that. And this integral is left with d phi. So it's a phi integral. And r doesn't care about the phi. B is a constant. So, if you look at this side, there's a term multiplied to the current. And the reason why we have this is because the amount of current will change inside the gray inductor in the center, because the total thickness, or the total surface area of the gray conductor, is pi a squared, because a is the radius of the gray part of the conductor, and r is just a variable. So depending on where you are at between 0 and a, the r can vary from 0 and a. So you have to figure out the ratio between the total amount of current, which will be based on this a radius, versus whatever radius that you apply. Okay, so you can now see that this r will vary from 0 to a. Okay, so it could be 1 or it could be less than 1, depending on what the r is. So that's a general expression of the current, and if you do this calculation, you get 2 pi r b phi equal to, these pi's will cancel out, so you get r square over a square as shown here, and the b, if you solve for the b phi, you get this expression, where the B field, the magnetic flux density in the phi direction, is going to be proportional to the amount of current flowing, and the R, the radius of the conductor, the location in which, this is not an actual radius, but it's the location indicating the amount of current flowing inside the center conductor. And this is a constant value of the conductor. And so this is a scalar, because there isn't any hat or any vector applied to it. You need to multiply the a phi unit vector to get the b hat. So that's the magnetic flux density inside the conductor, and you can see that it'll vary depending on where you are measuring the B field. So for instance, if you're measuring the B field at a radius very, very close to the center, if your radius is right here, the B field is very low. But if you go out and measure right here, then the B field will be maximum, because it's now enclosing all the current that is flowing in the conductor. So if you go down now, that's why it varies depending on the location of the R where you're measuring it. The second thing we need to do is calculate the B field outside the center conductor. So the location of the measurement will be from A to B, okay, greater than A and smaller than B. So if you look at the picture again, it's greater than A, so, and smaller than B, so it'll be between this gap. Okay, that's where the B field we're trying to measure is. So we're not gonna, if you look at this, the equation is exactly the same, except that the current is just fixed, because if you apply the R, if you apply the contour over here at this white space between A and B, then regardless of what the R is, the amount of total current is already total, right? The amount of current is still I, regardless of where you're measuring at in this white space. And therefore, um, 2 pi r b phi is mu naught times I, and so the b phi is mu naught I over 2 pi r, and the vector version of the b phi is this times the a phi unit vector. So that's the outer conductor, B field out of the conductor, out of the central conductor. So that's how we found the B fields everywhere. The next thing is the interesting part, because we need to figure out the magnetic flux that could link with the current in the ring form. In the ring from R to RdR. So what does this mean? So if you look at this gray conductor, this is a magnified version to illustrate it. But if you look at this thin central conductor closely, you can dissect the current. So the current is flowing into the plane, into the screen, but we can now dissect this thin conductor into very, very thin rings like this. And this is just one ring, okay, and it has the radius of r, and the thickness of that ring is dr. Okay, so that's where current is flowing. And we can also say that this is another ring right outside, and there will be many of these rings inside this conductor. And if you think about this ring, the current is flowing into the screen in the form of a cylindrical wall, but we also know that because the magnetic flux is flowing inside like that, and also outside like that, and outside the conductor like this, the magnetic flux is flowing like that. And so we need to figure out the flux linking with the current flowing in this ring. Okay, so this is how we're going to do it. So we already calculated that there is a B1 and B2 previously. B1 is inside the conductor and B2 is outside the conductor magnetic flux density. And so if you're trying to figure out the magnetic flux that is engaged with the current flowing in this ring, you have to account for the B1 field, okay? The B1 field that is from R to A, which means that magnetic flux that is flowing from here to here, okay? R to A. And then you have to um, take into account the magnetic flux flowing between A and B, this area, okay, this whole area. So that's why we need to now integrate from these limits, between these limits for both B vectors, okay? And you can see that we have the expression for the B phi 1 and B phi 2, which we have it in the previous slide over here, these guys. And so you can plug it in over here. And then if you do the math, then you get this expression. Okay, that's the expression for the flux per unit length. um, Yeah, so a quick side note, the current is inside the ring. The amount of current that is inside the ring is basically the surface area of this ring um, divided by the circular surface area, because that's the ratio, right? And multiplied by Ri, because I is the total current flowing in this gray area. And so you can see that it's a pi a squared. That's the total surface area of the gray circle, and 2 pi r is the length of this circle, and you need to multiply with dr, which is the height of the circular ring, to get this curved or rectangular shape. That will give you, and the pi's will cancel out, and that will give you the I times 2r dr over a square. So that's the amount of current inside this ring. Okay, and you can see that the amount of current will change depending on what the R is, because the R will move from 0 to A to account for the whole ring inside the circle. And so based on this equation that we just derived, and based on the current inside the ring, the flux linkage of the ring is basically um, um, the yeah, the flux linkage of the ring is not just yeah, you can multiply the ratio of the current, because it's um the this is basically the number of turns, right? Because before we have multiplied the number of turns with the flux to get the flux linkage. But in this case, there is only one turn, because this is a single conductor. But we have multiple rings inside, so we have to express the amount of current flowing in a single ring, which is expressed by this. So that needs to be multiplied with the flux per unit length, and that gives us the flux linkage of the ring. Okay, and so this guy is this. So if you replace, you get this equation that's multiplied. And in order to calculate the total flux linkage, you need to add all the tiny bits of the flux linkage over from 0 to A, because if you look again, we are dissecting these gray areas into multiple rings, and so we have to integrate from 0 to all the way to A. That way we're going to cover the whole gray space. So that's why we have this equation, and the rest is just math. You just plug in this equation into the integral like this and do the integration, and then you get, and if you do the math, you can follow this later, you arrive at this equation. Okay, so now you see that the total flux linkage is given by this equation. So the final step is to find the inductance by dividing the total flux linkage with the current. Okay, and we're talking about the inductance per unit length. That's why there's a slash division by L. But if you do that, then you'll notice that the L, basically you have to get rid of the i's, because you're dividing with that, and then you get this L. So the inductance per unit length L is given as follows. Okay, if you have lengthy cable, you'll notice that the inductance will continue to increase because the length of the cable, if it's longer, then the L will increase and therefore the total inductance will also increase. There are two sections to this inductance. And the first one is the flux linkage internal to the solid conductor. And we call this internal inductance. So even if you don't have the outer conductor, okay, in the case where you don't have this outer conductor, but if you just have a bare wire like this, okay, that's the inductance that you will measure is going to be mu naught times L divided by 8 pi. Okay, if you're given a, you know, copper conductor or something like that, this is the self-inductance of that copper bare conductor without any outer conductor surrounding it. And you can see that it's only a function of length. Okay, so the longer the wire, the more self-inductance you get. Okay, but if you have a coaxial cable, this part plays a role, and you can see that it is the you can change this value by playing around with the radius values of B and A. And if you basically make the A much greater, then the whole thing will go to 0, uh, and it'll act like a bare conductor. But if you don't, if you have a significant amount of B, then you'll increase this value. And also this also increases, the second term also increases with the length of the cable as well. So there are two components again, the internal conductance and the internal inductance and the external inductance, that is the linkage of the flux between the inner and the outer conductors. So another example is a case where you have just two wires, laid on a ground or placed somewhere. Um, and if you want to find self-inductance in this case, how do we do that? So a very similar process is going to be taken, um, because you will notice that one conductor has a current flowing in the one direction and actually in the z direction, and the other current is flowing in the negative z direction. So if you align your thumb on this current, the rest of the four fingers are going to wrap around this conductor like that. Okay, and if you align your thumb with this current, the four fingers will wrap around like this. Okay, so if you see over here, both of the magnetic fields, okay, one is going this way, so it's going up here. The other is going down and up, so it's also going up. So you'll notice that the magnetic field here is in total going upwards. Okay, so first you got to note that. Um, so the internal self-inductance of a long wire was determined in the last example. In this example, we said that we derived that the internal inductance of a bare conductor is mu naught L over 8 pi. So that applies to these guys. Okay, mu naught L over 8 pi. So we need to leverage that. And there are two wires. So the total internal self-inductance is times 2. So this times 2 is mu naught L over 4 pi. Okay, because there are two conductors. Now we need to calculate the external inductance because there are two wires. So between the two wires, the magnetic flux density is created in the y-axis direction. We have already discussed this. If you apply a right-hand rule, we know that the magnetic field between them is pointing upwards in the y-axis direction. So now you can see that there are two contributions in the y-axis directions, but in total there are only purely y-axis directions. So it's a AY, that's the unit vector, with two contributions coming from the first conductor and the second conductor. So that's the B equation. And if you apply the Ampere's law um, to conductor number one, um, so meaning that you will, uh, imagine circulating around this conductor like this, um, and that's what this expression is telling us. If you circle out around the first conductor magnetic flux density like this, that will equal to the total amount of current enclosed in that circulation, which is I, right? And it's the same thing happens for the second conductor. If you circle around the second conductor, the total amount of current enclosed is I as well. And so now, if you do this calculation and say that we're going to measure the B field at this x-axis location, this random x is going to determine the distance between the first conductor, and also it'll determine the distance between the second conductor like this. So the first distance will be x, the other distance will be d minus x, right? So you can now see that there is 2 pi x, that's the contour of the x-axis radius, right, times the by equaling this current. And in the second case, you have, instead of x, we have d minus x. Okay, that's the radius of this contour. Okay, and this is the radius of the first contour. So you have these two different lengths, and that equals to the b values contributed by the two conductors, and you can see that mu naught I times 2 pi x, and the other is mu naught I divided by 2 pi times d minus x. Okay, so so that's how we calculate the B field. We need to now calculate the flux. Because we know the flux density, we can calculate the flux between the wires, and in order to calculate the flux between the wires, you have to know what this area is. If you know the surface area of this part, you just need to multiply the surface area with the B vector that we just derived to get the flux. Okay, the flux density and also the flux itself is going through the two wires like that. And so how do we do that? We've got to integrate the B field, and we need to integrate in terms of surface. Okay, so the surface will be from 0 to L. That is the length. Okay, that is the length 0 to L. That's the length, and we need to integrate from um, the radius A to d minus A. Okay, this area. Okay, this length is A to d minus A because the radius of this circle is A. So that's why you see now there's another integral from A to d minus A. Now we need to define what ds is. ds is a tiny portion of the surface area between these two wires. So it's a tiny portion. This is a ds, and ds is a multiplication of the x-axis and the z-axis direction. Right, this is the x and this is the z-axis direction. So you have to multiply dx and dz. Okay, you have to multiply dx and dz. Okay, but the normal vector will be in the ay direction. Okay, so that's your surface differential surface vector. So that is shown here, dx, dz, and ay. That's your ds. So now plug this inside here and plug the definition of the B vector, which is dissected into two parts as shown here. Um, and of course, they're collectively in the y-axis direction, so you have to multiply AY to both of them and add them. And if you do that, then you have the addition of the two components multiplied by AY, and ds is shown here, so there's another y. So the two AYs become 1, and you have to just integrate from in terms of x-axis and the z-axis. So if you do the math, then you get to this equation right here, where you now have the flux, magnetic flux, expressed in terms of this. You can now see that the amount of flux passing through the two wires will increase if you increase the d, which is the distance between the two wires. So if you move this second wire away and place the wire over here, then you have a wider surface area, right? So the amount of flux increases because you have more space. If you create more space, you have more flux flowing through it. And of course, if you have a longer line, then also the surface will increase, and therefore you have more flux. Okay, so if you just keep that in mind, and the length and the d will change the amount of flux. If the d, the distance between the two wires, are much greater than the a, the radius of the wire, which can be in a lot of cases, that should be the case. In that case, if d is so much bigger than a, it'll dwarf the a, so it'll be similar to not subtracting the a at all because d is so big. In that case, we can remove the a and only use d over a. So in this second equation, you can see that minus a disappeared, and therefore it's proportional to d. And don't care about a because if the a is so small compared to d. The last step is dividing the flux with the I that created the flux to get the L. And yeah, so of course, before you do that, you have to calculate the flux linkage, which is the number of turns times the flux. And the number of turns in this case is 1 because there's only two wires. It's not a coil, so there's only two wires. And you can almost think that this is just a single turn, right? So n is 1 in our case, but by definition you have to write n times pi. And dividing that with the current will give you the L. So now if you plug in the definition that we derived and divide by with I, the I and this I will cancel out and give you this equation. And so you'll notice that the inductance between two wires will increase if you have a greater distance between the wires and if you have longer wires. Okay, so if you want to minimize the parasitic inductance, okay, this is an inductance typically that you don't want. In that case, when you design a circuit, you got to make sure, let's say you have a PCB board that was designing current path, current traces on the PCB board. You have one current trace, then you better make sure the next current is not that far away. Instead, what you will do is create a trace right next to each other so that the surface area between the two are minimized. That is one way you can reduce the amount of inductance, parasitic inductance, that you don't want in your system. So now you can see that the total inductance is internal and also external. The internal inductance, again, was calculated previously, but the internal inductance is just internal to these two conductors, and that was defined by this. but because we had two conductors, we multiplied 2. That's why you see a 4 pi at the denominator instead of 8 pi, and the external inductance is something we just derived right here. So here's another example. If you have this, now we have two coils, and so they'll be interacting with each other. Um, so one coil is wound in the smaller cylinder, a thinner cylinder, and there's another cylinder that goes over the smaller cylinder, and there's a second turn. So you'll notice that if you apply your four fingers and wrap around these wires, your thumb will be pointing this way, okay, due to the right hand rule and the direction of the current. One thing to note is that all the current, all the magnetic flux flowing through this core will also flow through these wires, okay? All the magnetic flux flowing through the generated by current number 1 is going to go through these second wires, okay, which has a current of I2 and the number of turns of N2. The first coil has a number of N1 turns and the current is I1. Length is L1 and length is L2, and the radius of the core is A, and the material has a relative permeability of mu r. So similarly, we're going to apply a cylindrical coordinate system around this cylinder because it's a cylinder already, and this will be the z-axis of that cylindrical coordinate. And so if you apply the Ampere's law and calculate the amount of B field internal, there will be B field flowing inside this core material. So that'll be B1, and DL will be something around this core. And this contour will enclose, well, no, sorry, you can't do that, right? If you have the contour like this, you don't have any puncture of the surface area with the current, right? If you apply a contour right outside the core, there's no puncture of current through this surface area, so the answer will be 0. So you need to make this kind of contour, and in this surface area there are 1, 2, 3, 4 current passing through it, right? So that way you can express in terms of this equation. So that contour will enclose current number 1 in the amount of N1. Okay, let's say there are N1 turns total. So if you apply this green box around like this, then you know that the total amount of current is N1 times I1. And yeah, because the mu r of this core material, you have to put the mu r value there. Now let's do the integration. So there are two sections, because we're going to, again, if you look at this box, we're going to reduce the height. So this will go to 0, so there will be left with only the horizontal path of the green box, and therefore you have to move from 0 to L1, okay, 0 to L1, and then you have to come back, right? So if you do 0 to L1, you have to plug in the BZ, AZ, okay? And then the DL is going to be DC times AZ, because you're inside over here moving that way. When you're returning, you're going to be outside the core and you're going to be in the negative direction, and therefore you have to now multiply with the negative DC AZ. That's your DL in the outside of the core, and you're moving from L1 to 0. So L1 over here to 0, you're moving back. But when you're moving back, because you're outside the core, there isn't any BZ. So the BZ will go to 0, therefore this term is all gone. So now if you do the calculation, you note that it's BZ times L1, because if you do the integration, it's L1, and that'll equal to mu naught times mu r times I1 times N1. So BZ is this, and the B vector and the number 1 induced by the current number 1 is going to be this times AZ. Once you've figured out that current magnetic flux density, we need to figure out what the magnetic flux is. And all you got to do is multiply the surface area where the magnetic flux density is. So the magnetic flux density is inside this circle, moving that way. And so you need to multiply the circular surface area, which is pi a squared, to the B1. So pi a squared times B1 is going to be this. Okay, and we know that all of the flux generated by current number 1 is going to be linking with coil number 2, and so we just need to multiply the flux linking with the number of coils in the second circuit, which is N2, to get the flux linkage that has been generated, flux generated by number 1 current linking with number 2 circuit. Okay, so if you express this using this term, you get this expression. So we can see that the flux linking flux linkage in the second circuit is proportional to I1, because I1 is the guy who is generating the flux that will go to the second circuit and link with that second circuit. So if you're asked to calculate the mutual inductance, all you got to do is divide this guy with I1 that created this flux linkage. So if you divide the I1 and rewrite, you get the mutual inductance expressed like this. Yeah. So you'll notice that the mutual inductance will change depending on the number of turns, basically, and the surface area of the circle, of the circular surface area of the cylindrical circle. And also note that the mutual inductance are mutual, so it's L12 is equal to L21. Okay, now let's talk about magnetic energy. Just like capacitors storing energy in the form of electric field, inductors can store energy in the form of magnetic fields. So if you consider a single loop, okay, a small loop like this, with a self-inductance L1, so if you have this loop, it'll have a self-inductance, right? Because if it's a conductor, so all conductors have their own, self-inductance. And if you increase the current I1 from 0 to I1, okay, if you look at this chart, and if you try to increase the current like this from 0 to I1 like that, then you have this voltage that is generated across the loop, because if you we learned, you would have learned before, that according to the Lenz's law, if the magnetic flux tries to increase, it induces a reversed voltage to block that magnetic field from increasing, and that's in the form of V1. So if you have an inductor, you would have learned that the voltage across the inductor voltage across the inductor is given as the L1. So this is just a single loop inductor. It's L1 times the slope of the current, which is di1 over dt. Okay, so if you increase the current from 0 to I1, we know that an EMF voltage in the loop that opposes the current change will occur. Okay, and so that's the amount of voltage that would induce due to you trying to increase the current in the loop. So basically, work must be done to overcome this electromagnetic electromotive force. Okay, EMF and MMF, right? Magnetomotive force. These are the two voltages that either drives the electrical circuit and the magnetic circuit. And this is a electromotive force, so it's a voltage. And so, if you try to calculate the work, the energy, you need to integrate the power, right? Power is in watts. So watt times second, watts second is joules, and power is V times I. And we know that we want to have the I flowing in the circuit, and we know that this amount of voltage is induced due to trying to push I through the current, the loop. So this is a voltage and this is a current. And if you do the math, you'll notice that the dTs will cancel out. And therefore, this equation becomes like this. And so we're increasing the current from 0 to I over I1. And so if you do the math, then you get the 1 over 2 Li squared. Okay, this is a very simple equation that describes the amount of magnetic energy stored inside this tiny loop. So the magnetic energy is 1 over 2 Li squared. And this is probably something you guys have learned previously in other courses. If you have two loops or many loops, we're going to go to many loops, but let's now consider there are two loops. So initially at time 0, current in both loops are 0. So I1 is 0 and I2 is 0. So there are no currents in any of these loops. But first, if you raise I1 to capital I1, if you start to flow current through this first loop, you get the magnetic energy of 1 over 2 Li squared. Okay, but in the magnetic energy in loop 2 is still 0 because there isn't any current yet. Okay, under that situation, if you raise I2, if you also increase the current in the second loop to capital I2, you get the second magnetic energy, which is 1 over 2 L2 I2 squared. Okay, but when you do this, some of this flux, flux will be, generated by the I2, so flux will come out and link with C1. Okay, and when the flux links with C1, then it's going to induce a voltage because there's a variation in flux, then you induce a voltage. And so electromotive force, which is a voltage of V21, and if you look at the subscript here, it's V21, so current in coil number 2 is inducing voltage in number 1. Okay, that will depend on the inductance between the two coils times the time variation or the slope of I2. Okay, so you note that you need to note that the magnetic flux, magnetic energy between the coil 1 and 2 is now going to be expressed in terms of the voltage uh, V V21, which is current number 2 inducing voltage in coil 1 times the coil 1 current, which was already there. Okay, because coil 1 is already there, but now there's a separate, um, another coil inducing generating magnetic flux to link with coil number 1 inducing extra voltage. So the current needs to be multiplied with that extra voltage, which is V21. So you get the power, and then if you integrate it over time, you get the energy. And so if you do the math and plug it in, you get L21 I1 times I2. So that said, the total magnetic energy is the self-magnetic energies of W1 and W2 and the mutual magnetic energy, which is L21 times Li1 and I2. So instead of 2 loops, if there are n loops, this expression can be generalized and expanded to n loops. And you can see that the total magnetic energy is going to be 1 over 2 with the summation of all of this. So you'll have to put J1 first and then sweep the K from 1 to n. Okay, if it's L1, 1, and L12, L13, all the way to L1n. Okay, you need to add all of them up. But you got to note that if the mutual inductance are equal, so LJK is a LKJ. That's why you don't see a 1 over 2 over here, okay? Because there will be always 2, and the 1 over 2 is going to be canceling out the 2 eventually, making it into a 1. So this is a general expression for n loops. And if you look at the magnetic energy in terms of field quantities, we know that the vector magnetic potential, this is like the voltage in the magnetic field domain times the current density. Obviously, that would lead to energy. And we have seen H times B, that's the hysteresis curve, right? When we were talking about the different magnetic materials in soft and hard magnetic materials, we looked at the hysteresis curve, and I mentioned that the surface area of that curve is a energy loss per volume. So if you multiply the two and integrate with the volume, then you get the loss, the magnetic energy that way. Also, utilizing these definitions, now you can have, instead of H, you can have B divided by mu. So that'll give you B squared over mu. And oppositely, if you use the fact that B is mu times H, you get mu H squared. Okay, all 4 of these equations will give you the amount of magnetic energy.